So relative strengths of acids and bases. Now we already know what is a strong acid and a weak acid, etc. Right? So let's just revisit those concepts in light of the Arrhenius concept and Bronsted-Lowry concept we learned in previous. So what is Arrhenius concept saying that an acid is a substance which gives away H plus ion in solution, right? So let's say we have HCl and HCl in the gaseous form and we are dissolving it in water. Okay, and we know HCl is a strong acid, so there is a single arrow I'm drawing. It converts into H3O plus ion, hydronium ion, and Cl minus, that is chloride ion, right? So because it dissociates completely, it is a strong acid. Okay. Now, what are other strong acids? Let us say H2SO4 sulfuric acid, HBr hydrochloric acid, okay, hydroiodic acid, also called hydrogen bromide if it is in the gaseous state, hydrogen iodide. So that's same thing, right? Hydrogen chloride like that. Okay, and then we have HNO3 nitric acid and HClO4. Okay, which is orthochloric acid. These are all examples of strong acids. Okay, as per Arrhenius concept. Why? Because they all have hydrogen, so they can release H plus ion in solution. Now, similarly, a weak acid, we discussed this example CH3COOH, and when it is dissolved in water, now it's a weak acid, so we have reversible arrows to indicate dynamic equilibrium that will attain at a certain time after we mix or we dissolve acetic acid water. So this is liquid, okay, and H plus ion, which is aqueous, and CH3COO minus ion. Okay, this is what the acetic acid disintegration, and because it is a weak acid, therefore it will not completely dissociate into these ions, right? So similarly, like a weak electrolyte. So we are extending the concept of strong and weak electrolytes in the context of acids and bases. Okay. Similarly, if I talk about a base NaOH, NaOH we know is a strong base, right? Sodium hydroxide, and on dissolution in water, it dissociates into sodium ion Na plus and hydroxyl ion OH minus, right? So since it dissociates completely, it's a strong base. So basically it is a strong electrolyte, and because it is a base, therefore strong base. And why it is a base as per Arrhenius? Because it is releasing hydroxyl ion OH minus. Now on the other hand, an example of a weak base like ammonia, NH3 in aqueous plus, let's say we are dissolving in water. Now since it's a weak base, this is not a single arrow, this is a reversible arrow, and it will dissociate into hydronium ion NH4 plus and OH minus. So here water is acting as an acid, it will release H plus and OH minus, and that H plus will combine with NH3 to form NH4 plus. Understood? So basically this is a strong base sodium hydroxide, this is a weak base. Similarly, this is a strong acid hydrochloric acid, acetic acid is a weak acid. Agreed? Now we will understand the same relative strengths of acids and bases as per the Bronsted-Lowry concept also. So what is Bronsted-Lowry concept? We understood in the previous video that whenever a substance releases a proton, okay, in aqueous solution, it's a acid. A substance accepting a proton, okay, is a base. Correct? Now, similarly, in this concept, let us say a given acid is there, okay, like acetic acid. It exhibits different strengths in different solvents, okay, and those solvents are of varying basic strength, for example. So that means the strength of this acid is not fixed per se, it depends on the solvent it is in. Let us say we have this acetic acid and we are talking about it dissolving it in aniline, which is an organic compound. So this is the structure of aniline, okay, benzene plus ammonia, so aminobenzene we call it as. And because CH3COOH is a weak acid, so let's say it's a reversible reaction having dynamic equilibrium. And CH3COOH disintegrates into CH3CO minus plus this aniline becomes NH3 plus. So there is no aqueous reality because we are not dissolving it in water. Just note that. Now, whereas in another case, this CH3COOH, if it reacts with H2SO4, which is acid, now here CH3COOH is acting as a base. In the previous case, CH3COOH was donating a proton in the first case, therefore it was acting as acid when we are reacting with aniline. But the same CH3COOH, when we are combining with H2SO4, it's acting as a base. So what it will form? It should take a proton, right? So it will form this is CH3COOH. I can write like this also. Okay, so same thing. This double bond CO and this OH. So okay, and this OH is already repeated here. Okay, plus HSO4 minus ion. So sulfuric acid is a diprotic acid. We saw in the earlier case. It can release one hydrogen ion. It can release two hydrogen ions. In this case, it has released one hydrogen ion. Okay, and that hydrogen ion got joined to the acetic acid. So in terms of proton, what we discuss as it has released one proton. H2SO4 has released one proton, and that proton has clubbed with the acetic acid double bonded oxygen. See this one. This is double bonded oxygen. So it got connected to this, and we have we will write like this. It's O plus because now this is positively charged at this place. So we are not going into that detail in this video, but just understand here. In the first case, CH3COOH acted as an acid when we reacted with aniline. In the second case, the same CH3COOH is acting as a base. Okay, when we are reacting with H2SO. Understood? So it depends on the solvent also, and the relative strengths of different acids and bases when compared in the same solvent generally give us a better picture. So that same solvent generally is called water, and that's why we discussed aqueous solution. So in Bronsted-Lowry concept, we may define that relative strength of an acid is its relative tendency to lose a proton. So acid means losing a proton. So relative strength of acid implies we can say relative tendency of that acid to lose proton. Okay, correct. To what? Common solvent, in this case we said water. So common solvent we will generally take as water for comparison purposes. Okay. Now similarly, if we say any base, so relative strength of a base is nothing but relative tendency to accept the proton from water. Okay, understand this. These two things. Relative tendency of proton. Let us say we are talking about ammonia. We know it's a weak base, but let's just for the purpose of understanding. So H2O. So H2O splits into H plus and OH minus, and that H plus is accepted by ammonia to form ammonium ion. Okay, and this is when H plus is removed, so it will become hydroxyl ion. Okay, so relative strength of base I can measure as how much is the relative tendency of this particular base to accept the proton from water. Got it? In the next video, we will discuss something related with the ionization constant when we talk about acids and bases. So we basically talk about Ka and Kb instead of K. We will discuss that concept in the next video.